enregistré. Donc, I stop saying stupid things and welcome Jean-Marc to this COVID session.
Thank you. C'est obligé que je parle anglais.
Oui, bien sûr.
Parce que tout le monde parle
Je préférerais que tu parles anglais parce que non, mais ici, oui, mais il y a des gens qui vont t'écouter sur Zoom.
Sur Zoom, là, mais William.
Je pense que William doit parler français.
Et après, tout le monde parle français, parce que si tout le monde parle français, je vais parler français, ce sera peut-être plus facile.
Si tu as vraiment envie de te faire.
Ah non, non, moi je veux bien, mais il faut que ça ait un sens, quoi, parce que tout le monde parle français ici, il n'y a pas de souci.
Oui, mais je pense que ce serait mieux quand même.
Parce que les slides sont en anglais.
Oui, d'accord.
Mais à moins qu'en Zoom, il y a quelqu'un qui voudrait que je parle.
Il y a des gens qui vont arriver qui parlent anglais. En fait. À mon avis, il va y avoir
Federico, would you like me to speak English or it's okay in French? Non. Bon, je vais peut-être le faire en français alors.
De toute façon, ça ne prend rien que je dise ça. C'est moi.
Alors, je vérifie que ça marche. Ah oui, il faut se remettre dessus, non?
Donc, il faut cliquer sur la présentation.
Ah oui,
le slide blanc.
Ah, c'est ça.
Ah, voilà. Bon. Je le fais en anglais si tu préfères, hein. Je vois que tu fais la tête.
Non, c'est ça quand on est des invités prestigieux.
Bonjour. Bon, donc je vais essayer de rattraper le retard. D'abord, remercier Paul pour l'invitation et pour tous les efforts qu'il a fait pour cette conférence, parce qu'il en a fait. Voilà, et donc je vais parler d'un travail que j'ai fait en compagnie de William Kenge, qui est à Saint-Gilles, et puis de Camilla Carré, qui était avec nous à Paris 1 en doctorat. Et ça va être donc un sujet autour de la sélection de modèles. Comment sélectionner un modèle. Et puis, comme nous sommes dans cette conférence EcoDep tournée vers l'écologie, j'ai choisi un exemple de données de pollution. Donc ça, ce sont des données relevées à Marseille de particules fines. Donc, c'est les particules fines plus petites que 10 microns, choses comme ça, prises pendant presque 2 années. Voilà, donc presque 700 données. La question qu'on s'est posée, c'est comment choisir un bon modèle pour ce type de données. Alors, classiquement, choisir un bon modèle, c'est quand même disposer aussi, ça va être plutôt un modèle de série chronologique, et c'est disposer d'une famille de modèles dans lequel on va piocher pour essayer de trouver un modèle un peu optimal. Donc, par exemple, une famille de modèles admissible ici, enfin classique, ce serait de prendre parmi des processus d'IARMA ou GARCH. Essayer donc d'une famille comme celle-ci, en choisissant a priori, par exemple, qu'on puisse avoir des ordres jusqu'à 10, quel serait le meilleur ARMA ou le meilleur GARCH pour modéliser ces données. Bon, donc ça, c'est la question que nous nous sommes posée. Et alors, pour commencer, bon, ça, je vais peut-être passer parce que c'est classique. Je vais revenir un tout petit peu sur des familles de modèles un petit peu plus générales que les ARMA et les GARCH. Et donc, première famille de modèles que l'on pourrait considérer, ce sont des modèles linéaires, si on veut, mais écrits sous une forme un petit peu différente, où x de t s'écrit comme une combinaison linéaire potentiellement infinie de ses précédentes réalisations plus un bruit, plus une innovation. Et en fait, les ARMA sont un cas particulier de ce type de modèle. Voilà, les ARMA, où là, pour le coup, on réécrit la deuxième partie comme une moyenne mobile, mais en fait, on peut toujours revenir à cette écriture-là du moment que le polynôme ici est des racines dans de l'ordre discret. Enfin, bon. Ensuite, deuxième famille de modèles que nous pourrions considérer, et là aussi je vais donner un cadre un petit peu plus général, celui des arches infinies, ça a été développé par Robinson en 91, où cette fois-ci, x de t s'écrit comme un bruit blanc, là xi de t c'est un bruit blanc dans toute la suite, hein. Et puis il y a une multiplication par un écart type qui rend, on pourrait dire, instantané.
Pardon, excuse-moi.
Oui.
Est-ce que tu veux dire, il y a quelqu'un qui dit qu'il n'entend pas. Est-ce que d'autres personnes qui sont dans la session Zoom entendent ou pas?
Alors.
Ah si, apparemment ça marche.
C'est bon?
Oui.
C'est bon pour moi.
Merci, William.
C'est bon pour moi aussi.
Ah, parfait, merci. Et donc, ici, il y a donc une sorte d'écart type instantané qu'on appelle, que les économistes financiers appellent volatilité, hein, et qui s'écrit là aussi comme une fonctionnelle des valeurs passées. Bon, alors, comme ce doit être quelque chose de toujours positif, ici, les coefficients vont être positifs, et on va travailler avec des carrés. Et pour garder la cohérence, on met tout en carré. Donc ça, c'est ce qui a donné ces modèles conditionnellement hétéroscélastiques, puisque ici, on s'aperçoit que l'écart type conditionnel instantané dépend des valeurs précédentes, hein, ce qui permet de modéliser des changements un petit peu plus marqués dans les fluctuations locales d'un processus. Alors, un modèle particulier des arches infinies, en fait, c'est celui par lequel tout a commencé, hein, c'est donc plutôt ça va être les arches P, où pour le coup, cette écriture-là qui fait une somme infinie, elle s'arrête à l'ordre P. Et puis en 86, Bolersef avait rajouté quelque chose qui dépend de la volatilité au carré, mais ça peut aussi s'écrire comme un arche infinie toujours. Voilà, donc deux grosses familles de modèles un peu plus généraux que les arches, que les garches et que les armas. Donc, AR infini et arche infinie. Alors, la question qu'on s'est posée, c'est comment essayer de définir un modèle commun à tout ça, et puis peut-être à d'autres processus. Et le moyen qu'on a trouvé, vous avez vu, j'ai essayé de faire apparaître que x de t s'écrit finalement comme une fonctionnelle des valeurs passées, ou alors un bruit fois une fonctionnelle des valeurs passées. Eh ben, c'est un modèle général qu'on considérera ici, avec fonctionnel petit f, qui correspond en fait à une espérance conditionnelle par rapport aux valeurs passées du processus, et puis ici une autre fonctionnelle, grand M, que j'aurais pu appeler sigma, hein, qui est une sorte d'écart type conditionnel des valeurs passées. Voilà. Ici, xi de t, c'est un bruit blanc, hein, donc d'espérance nulle. Donc, on a ici tout ceci. On a une espérance nulle pour ce bruit blanc et on va supposer qu'il y a un moment d'ordre R pour le bruit avec R plus grand ou égal à 1. Donc, ces modèles-là, qui s'écrivent sous cette forme-là, eh bien, on va les appeler des modèles causaux affines. Alors, causaux parce qu'en fait, ils dépendent des valeurs passées. Et affine parce que vous voyez, quand on conditionne par rapport aux valeurs passées, on a une écriture comme une sorte de constante fois le bruit blanc plus une autre constante. Donc c'est une forme affine. Alors, en fait, on peut donner d'autres extensions à ces modèles-là, notamment un peu comme la même type d'écriture que les processus Garch. Zakoyan avait développé des T-Garch, hein, comme T comme threshold, comme un seuil. Donc, des modèles dans lesquels il y a un comportement différent de la volatilité suivant que les valeurs précédentes étaient positives ou négatives. Donc, c'est un modèle un peu asymétrique par rapport au passé. Et puis, ça avait été aussi généralisé finalement dans cette gamme de modèles qui s'appelle les APARCH ou les APGARCH, où il y a une puissance delta, ici plutôt qu'un carré, ou une valeur absolue. Et puis, là aussi, il y a une forme asymétrique, avec un coefficient d'asymétrie gamma i qui a lieu ici. Voilà, donc ça, c'est encore des extensions, mais tous ces modèles-là peuvent s'écrire comme des modèles affines causaux. Et pareillement, encore, si on combine des modèles entre eux, c'est-à-dire qu'on prend un arma, mais au lieu de prendre un bruit blanc pour l'arma, d'habitude, là, il y a xi de t, hein, eh bien, on va prendre un garche à la place. Donc ça, c'est ce qu'on appelle un arme à garche. Ce sont des modèles qui ont été utilisés en finance, hein, et développés pour la finance. On peut aussi faire des armas à parche, où là, on prend le bruit blanc, on prendra un bruit à parche. Bon, il y a encore plein d'autres possibles différents modèles de ce type-là, hein, qui pourraient s'écrire comme des modèles affines causaux. Donc, on a comme ça un modèle commun, joint pour tout le monde. Alors, une question qui se pose, c'est ces modèles assez généraux, comment savoir s'ils sont définis, et mieux que ça, s'ils sont stationnaires. Et ça va pouvoir être déterminé grâce, finalement, à un objet qui va être clé pour la suite, c'est de considérer les dérivés partiels des fonctions grand N et grand F. Alors, vous voyez, comme ce sont des fonctions qui dépendent d'une infinité de valeurs, d'une suite, vous avez donc une suite de dérivés partiels. Donc, on va supposer que ces dérivés partiels existent, hein, dans la suite, et c'est elles qui vont régir l'essentiel de la dynamique du processus. Et en particulier, on a repris un résultat qui avait été démontré par Paul et Olivier Vintemberger en 2007-2008. On a tout de suite l'existence de ces modèles. Lorsqu'on suppose qu'on a un processus, un bruit blanc qui a un moment d'ordre R, avec R plus grand ou égal à 1, il y aura toujours une solution causale. Alors, causale, ça veut dire qu'on va pouvoir l'écrire comme une fonctionnelle du bruit blanc, de toutes les valeurs passées du bruit blanc, hein, mais passées. Et puis, cette solution sera stationnaire, ergodique, ça veut dire qu'il y aura une loi des grands nombres, hein, forte, et en plus, avec un moment d'ordre R, dès que la somme, alors vous voyez, c'est un peu lourd à écrire, hein, mais si on prend ces différentes dérivées partielles, on va prendre leur sup, ici, et la somme de toutes ces sup de dérivées partielles, plus le bruit blanc, le moment d'ordre R du bruit blanc, voilà, la somme des sup de dérivées partielles de M, doit être plus petit que 1. Donc voilà.
Précisément, c'est une condition de contraction, évidemment.
Oui, c'est lié à une itération de Picard.
C'est juste le théorème fondamental de l'analyse pour bien, pour avoir le fait qu'une dérivée a des accroissements.
Oui, si tu veux, oui. Voilà, donc ça donne un moyen de traiter tout processus affine causaux. Alors, c'est malgré tout un gros outil, hein, qui ne donne pas, et même souvent ne donne pas des résultats optimaux. Hein, par exemple, alors je vois que Jean-Luc, tu peux faire. Bon. Par exemple, cette condition de stationnarité, quand on prend pour des AR infinis, elle donne cette condition-là. Par exemple, typiquement, si on s'arrêtait à P, hein, ce n'est pas la condition que vous connaissez pour un AR, hein, pour ceux qui sont familiers avec ça. On prend plutôt le fait que le polynôme ait des racines en dehors du disque unité, et c'est plus fin, cette condition-là qui élimine un certain nombre de solutions. Hein. Donc, c'est pareil pour les arches infinies. On se restreint ici pour que ce soit la bonne condition. Il faudrait qu'il y ait une somme des CIJ. Or, cette condition qu'on a là donne la somme des racines des CJ. Donc, on perd un peu. On perd un peu, mais on a quelque chose qui nous permet d'avoir, de pouvoir traiter tous ces modèles, d'avoir au moins des possibles nouveaux résultats. Par exemple, celui-ci, pour les arches infinies, ça n'existait pas. Au moins, on a pu donner une condition pour que ce modèle-là existe. Soit stationnaire. OK. Alors, dernière chose un petit peu dans les préparatifs, avant de parler un peu plus de sélection de modèles. Être affine causal, c'est intéressant parce que quand on est affine, on sait que quand on somme, en gros, bêtement, hein, deux modèles, deux fonctions affines, on reste affine. Ben, en fait, c'est ce qui se passe un petit peu ici. Quand vous prenez deux modèles affines causaux, hein, que vous prenez l'union des deux, ben, vous pouvez réécrire ça comme un modèle affine causal avec un autre paramètre et d'autres fonctionnels. Ce qui est intéressant, parce que quand vous prenez une famille finie de modèles affines causaux, vous pouvez toujours les réécrire à partir d'une seule fonction petit f, une seule fonction grand L, et un espace de paramètres θ qui est plus grand, certes, mais qui va être commun à tous. Alors, c'est compliqué à dire ça, mais c'est juste pour dire que, par exemple, quand vous prenez la famille des ARP, Un AR1, c'est un cas particulier d'un AR2. Voilà. En fait, on réécrit un peu des choses très communes, mais ça se généralise. Par exemple, on peut trouver un modèle commun à des Garches et des Armas. Voilà. Et un espace de paramètres dans lesquels, pour certaines valeurs du paramètre, vous aurez un Arma, pour une autre valeur de paramètre, vous aurez un Garche. Donc, voilà ce qui est dit là. Et ça, c'est grâce à cette structure un peu affine. Alors, désormais, finalement, on va considérer que notre famille de modèles, ça va être constitué de modèles petit m. Donc, un AR1, ce sera un modèle petit m particulier. Et finalement, ce sera un modèle, c'est quoi? C'est que dans le gros paramètre qui génère tout le monde, il y a des valeurs possibles et il y a des zéros. Il y a des endroits où il y a des zéros. Et donc, au final, comme on dira que le paramètre il a des coordonnées, eh bien, un modèle, ce sera choisir certaines coordonnées entre 1 et d pour lesquelles il y aura vraiment des valeurs non nulles. Et donc, par exemple, si je prenais un ARP, donc à ce moment-là, D, ce serait égal à P, et eh bien, un AR1, ce serait de prendre juste le sous-ensemble avec 1. Un AR2, c'est avec 1 et 2, etc. Okay, donc, c'est une autre manière de réécrire les sous-modèles de cette famille. Ensuite, on va dire qu'au final, pour chaque modèle, il y aura un espace de paramètres admissible qui sera finalement une intersection ici du gros sous-modèle dans lequel on pourra prendre n'importe quel θ de RD, ici donné par cette même définition que tout à l'heure, mais en plus, on va contraindre à avoir certains zéros pour certaines coordonnées. Bon. Alors, par la suite, on va maintenant aller vers une procédure de sélection de modèles, et donc on va définir un risque et cette procédure. Alors, pour définir cette procédure de sélection de modèles, on va revenir à une technique qui a été développée depuis les années 2000, pour les Garches en particulier, pour estimer le paramètre d'un Garche. Et cette technique, c'est ce qu'on appelle le quasi-maximum de vraisemblance. Alors, de quoi s'agit-il? Donc ici, j'écris les choses plus génériquement pour les modèles affines causaux, mais en réalité, c'était d'abord pour les Garches. Donc, on va supposer qu'il y a une trajectoire qui est ici avec un vrai modèle, on va appeler M étoile, et un vrai paramètre qu'on appelle θ étoile qui est dans RT. Alors, ce vrai paramètre, il y a des zéros pour, si jamais vous avez par exemple un Garche 2, et que vous considérez la famille des Garches, enfin Garche de 2, et que vous considérez la famille des Garches jusqu'à 10, des ordres 10, il y a plein de zéros partout pour les coordonnées qui ne servent à rien. Voilà. Donc, il y a un vrai modèle qui est là. Et maintenant, quand on prend un modèle avec θ qui est inconnu, ici, finalement, on revient à des estimations semi-paramétriques et même paramétriques. Si je considère la log densité conditionnelle, alors, qu'est-ce que c'est ça? Ça veut dire que je prends la loi de xt conditionnellement à xt-1, xt-2, etc., jusqu'à l'infini. Eh bien, comme vous avez ça, quand vous conditionnez par rapport à xt-1, xt-2, etc., ça devient une sorte de constante. Ça, c'est une sorte de constante, si on veut. Et là, vous avez xi de t, qui est le bruit blanc. Donc, vous avez en fait une fonction affine du bruit blanc. Et si maintenant, je suppose que ce bruit blanc est gaussien, on va faire cette supposition pour construire le contraste. Après, on l'oubliera. Donc, si vous supposez ça, à ce moment-là, eh bien, la densité de xt conditionnelle est gaussienne, et donc sa log densité va s'écrire comme ça. Là, vous reconnaissez, normalement, il y a exponentielle de moins 1,5, tout ça, là, voilà, et puis là, il y a 1 sur racine. Bon, OK. Ça, c'est une log densité gaussienne. Donc, on a fait cette supposition. Alors, on s'aperçoit qu'ici, on a une log densité qui va dépendre des valeurs passées, mais jusqu'à l'infini. Ça n'est pas une statistique observable. Quand on travaille à partir d'une trajectoire, on ne connaît pas tout. Et donc, on va remplacer ce qui n'est pas connu par des zéros. C'est-à-dire que x0, x-1, x-2, qu'on n'observe pas, on va dire que c'est 0. Ce qui fait qu'on approche cette espérance conditionnelle là, et cette écartique conditionnelle, on les approche par ces valeurs-là, par ces statistiques-là, ce qui fait qu'on considérera ce qu'on appelle une quasi-log densité conditionnelle gaussienne, hein, où on a remplacé par. Une fois qu'on a fait ça, on peut maintenant calculer la quasi-log vraisemblance, qui va être la somme de toutes ces log densités, quasi-log densité conditionnelle, et prendre l'estimateur qui va alors maximiser ici cette quasi-log vraisemblance. Et c'est ce qu'on appelle l'estimateur de quasi-vraisemblance gaussien, puisque le contraste qu'on a choisi est par rapport à une loi gaussienne pour le bruit blanc. Voilà, donc ça, c'est quelque chose qui a été très développé au début des années 2000, notamment par Perkush, par Franck et Zakoyan, pour les Garches, et c'est ce qui est utilisé basiquement désormais pour estimer les paramètres d'un processus Garche. OK. Alors, ce qu'il faut savoir, c'est que même si on a construit le contraste à partir de quelque chose de gaussien, désormais on l'oublie. On peut travailler même si on n'est pas gaussien. C'est un peu ce que vous faites quand vous faites des moindres carrés, bêtement, en régression. On a construit ce contraste, on peut dire que le contraste a été construit à partir d'une technique gaussienne, hein, c'est le maximum de vraisemblance gaussien, et après vous oubliez, vous pouvez quand même utiliser des moindres carrés, même si vous n'êtes pas gaussien. C'est ce qu'on va faire désormais. Mais pour commencer, cette idée de quasi-vraisemblance et quasi-log vraisemblance va nous suggérer l'idée d'un risque. Hein, donc ça, on va prendre comme risque, finalement, moins de fois l'espérance de cette log densité gaussienne. Voilà. Donc on va prendre ça. Donc là, c'est l'inverse d'une vraisemblance, enfin d'une densité. Hein, ça a une forme un peu de contraste, si vous voulez. C'est quelque chose qu'on a envie de minimiser. C'est bien la forme d'un risque. Et donc ça, c'est ce risque-là qu'on peut définir théoriquement. Hein. De toute manière, c'est une espérance, on ne sait pas ce que ça vaudra. Et donc, on le fait par rapport à ces valeurs, même s'il y a des choses non observées, ce n'est pas un problème. Donc ça reste théorique. Si on rajoute une hypothèse ici, qui est une hypothèse classique, comme quand on fait de la vraisemblance ou du DM estimateur, hein, on va supposer qu'il y a une forme d'identifiabilité des paramètres, il y a une forme de bijectivité en réalité dans les fonctionnels, eh bien, on va pouvoir toujours, quand vous avez une valeur prise par fθ et une valeur prise par mθ, forcément, vous n'avez qu'un seul paramètre. En gros, l'idée qui est sous-jacente, c'est ça. Donc, comment on l'écrit? On écrit que si fθ égale fθ', et si mθ est égal à mθ', alors forcément, θ égale θ'. Donc, ça, c'est très classique. Et donc, si on a ça, on peut montrer qu'il va exister un unique minimiseur du risque pour chaque modèle. Hein, et clairement, si jamais vous avez votre modèle qui contient le vrai modèle, eh bien, à ce moment-là, le minimiseur de ce risque, ce sera la vraie valeur du paramètre. Hein, voilà. Mais lorsque vous êtes dans un cadre d'un faux modèle, un misspecified, eh bien, à ce moment-là, vous allez obtenir autre chose. Imaginez, typiquement, votre vrai modèle, c'est un AR2 et vous voulez l'estimer avec un Garche 1,1, eh bien, vous obtenez, certes, des valeurs de paramètres, mais qui ne sont pas du tout les vraies valeurs du paramètre. Bon, alors, ce risque, il est théorique, il va nous servir dans les calculs, mais en réalité, on ne pourra l'approcher que de manière empirique. Et donc, on va basiquement essayer de l'approcher par sa moyenne empirique, si vous voulez. Mais cette moyenne empirique, une nouvelle fois, elle n'est pas forcément très intéressante parce que dedans, hein, si on revient à cette écriture de ce qu'on appelle gamma, il y a ces deux objets qui peuvent dépendre de valeurs non observées. Et donc, on va plutôt considérer un risque calculable qui sera cette moyenne empirique où on a approché finalement moins 2 fois la log de densité, parce qu'ici on travaille avec moins 2 fois la log de densité conditionnelle. Bon, voilà. Et au final, on retrouve que minimiser ce risque empirique calculable, c'est aussi retrouver l'estimateur du maximum de vraisemblance, sauf que là, on peut le faire aussi pour n'importe quel modèle. Et donc, oui, vous allez pouvoir estimer le paramètre même quand vous vous trompez, hein, même quand vous n'avez pas le vrai modèle ou quand vous êtes en surparamétrisation avec un modèle plus gros qu'il n'est en réalité. Bon, ça, c'était pour définir un risque. Et maintenant, assez classiquement, le choix de notre procédure de sélection de modèles, ça va être de prendre le risque et puis de rajouter une pénalisation. Alors, qu'est-ce qu'on va appeler une pénalisation? Ça va être une fonctionnelle qui va partir d'un modèle, un des modèles de la famille, et donc la seule chose qu'on va lui demander à une pénalisation, c'est d'être croissante. C'est-à-dire que quand vous avez un modèle qui est inclus dans un autre, eh bien, la pénalisation de M1 est petit ou égale à la pénalisation de M2. Voilà, c'est tout ce qu'on lui demande pour l'instant. Et notre procédure donc, de choix de modèle, ça va être de prendre ce risque empirique calculable, ici, pris en la valeur de l'estimateur par quasi-maximum de vraisemblance, et on rajoute une pénalisation en fonction du modèle. Donc, quelque chose, c'est un risque pénalisé, c'est classique. Et on va donc choisir comme modèle pour la pénalisation peine, ici, celui qui va minimiser ce critère pénalisé. Donc, rien de nouveau par rapport à ce que vous connaissez si vous avez déjà fait des AIC, des BIC, c'est le même type d'écriture en réalité. Sachant que ça se comporte comme moins de log de la vraisemblance d'une certaine manière. Donc, c'est vraiment l'écriture classique de type AIC, BIC, sauf qu'on se permet de prendre une pénalisation plus générale. Alors, naturellement, ce qu'on voudrait minimiser, c'est le risque, ici, qui n'est pas accessible. Et donc, l'idée, ce serait d'essayer de trouver un modèle idéal, ou un estimateur idéal du modèle, qui serait celui qui minimise dans la famille de modèles le risque pris en l'estimateur de quasi-maximum de vraisemblance. Et donc ça va nous donner l'idée d'une pénalité idéale. Cette pénalité idéale, vous voyez, si je prends cette écriture-là, que je rajoute cette pénalité idéale, je retombe bien sur ce que je veux minimiser ici. Hein, vous prenez ça, vous rajoutez ça, les deux s'éliminent, il ne vous reste que ça. Donc la pénalité idéale qui est ici, qui n'est pas accessible d'un point de vue calculatoire, ce n'est pas une statistique, donc a priori elle reste un petit peu lointaine, eh bien c'est celle qu'on souhaiterait pour essayer d'obtenir ce modèle idéal. Bon, alors maintenant je vais donner plein de résultats. Je fais des présentations et on va voir que même si on n'a pas accès à cette pénalité idéale et à ce modèle idéal obtenu à partir de la pénalité idéale, on va quand même pouvoir dire des choses au moins asymptotiquement. Alors, je balance ici plein de choses. Ce n'est pas très agréable. Donc, on va supposer, il y a plein d'hypothèses qu'on est obligé de faire, qui sont un peu lourdes. On va supposer d'avoir au moins un moment d'ordre 8, ce qui est beaucoup. Donc, ça, c'est une des faiblesses de notre modèle, de notre démarche. On va supposer cette condition d'identifiabilité que j'ai déjà évoquée. On va supposer que l'écart type conditionnel forcément ne touche pas 0, ça c'est nécessaire pour la technique de quasi-maximum de vraisemblance. On va supposer, donc ça c'est plus classique, que tous les minimiseurs de risque sont à l'intérieur de l'ensemble pour éviter d'être sur le bord. Ça c'est classique en estimation par maximum de vraisemblance ou par estimation. Ils font ça aussi.
Ils se passent de ça, ils s'intéressent beaucoup aussi.
Ah oui, c'est vrai, oui. Ils font aussi le cas où ça vaut 1 d'ailleurs. Et ensuite, une hypothèse encore plus forte, en tout cas plus pénible à écrire, qui va être de supposer que les dérivées partielles par rapport au xk, df, mais aussi leurs différentes dérivées partielles par rapport à θ, ou les dérivées secondes, ce qui est assez classique en estimation, vont finalement décroître suffisamment vite. Ce qui d'ailleurs, pour ceux qui sont familiarisés avec ça, empêche d'avoir de la longue mémoire. On ne peut pas obtenir de longue mémoire dans nos travaux. Mais en fait, pour tous les processus classiques, comme les armas, les garches, les aparches, la décroissance de ces dérivés partiels est exponentielle. Hein, ça décroît exponentiellement vite, donc on n'a pas de souci. Tout ça, c'est vérifié dans ce cadre-là. Donc ça, finalement, ces hypothèses sont lourdes, mais c'est les plus faciles pratiquement à obtenir. Voilà. Et puis, il n'y a pas du tout, en plus, la clause du plus petit que 1 qu'on avait tout à l'heure. Hein. Donc, on s'abstrait de tout ça. Donc, finalement, vous pourrez aussi travailler en disant que c'est stationnaire sans avoir la condition boucan qui est très mauvaise. Et puis, finalement, revenir à ça où là, on peut se permettre d'aller bien plus, avec des valeurs bien plus grandes.
De toute façon, c'est toujours un problème. C'est-à-dire qu'on a toujours des mauvaises conditions quand on peut avoir
des choses très générales.
Ce qu'on avait fait une fois, c'était faire des variations autour de modèles par des conditions qui sont beaucoup plus strictes.
Oui.
Et en fait, avoir juste une variation comme ça. On a fait ça avec un séquence de
D'accord. Je poursuis. Donc, avec toutes ces conditions un peu moches, hein, mais qui sont classiques en M estimation, sauf la condition au moment d'ordre 8, là, c'est très top. Puis, il y a une autre condition. Là, on obtient, pour tout modèle, qu'il y a une convergence vers le paramètre qui minimise le risque. Donc, il y a un théorème de la limite centrale ici, et vous avez des matrices asymptotiques qui interviennent et qui sont ici, quand vous êtes en surparamétrisation, il y a une des matrices qui simplifie, sinon on est sur une matrice qui est une somme de covariance. Voilà, donc c'est un résultat qui a d'intérêt de généraliser ce qui existait déjà quand on travaillait avec le vrai modèle. On avait déjà obtenu des choses quand on fait de l'overfitting, et là, on l'a aussi même quand on se trompe. Donc, c'est ça qui est assez étonnant. Même quand vous vous trompez, vous êtes quand même intéressé. Bon. Donc, tout ça, c'est valable pour tous les modèles, ARMA, ARCH, APARCH, ARMA, GARCH, tout ça. OK. Donc là, maintenant, je vais aller vers des résultats de sélection de modèles. Donc, ça, c'était les prémices. Première chose, grâce à ce résultat, on montre ici que asymptotiquement, l'espérance du risque, c'est M étoile. Ça veut dire qu'en gros, cette technique qu'on a là nous fait asymptotiquement, normalement, en espérance, on va retrouver le vrai modèle. Voilà ce qui est dit ici. Bon, donc ça, c'est déjà une assurance agréable. Mais plus intéressant comme résultat, c'est cette pénalité idéale dont on peut donner un petit peu le comportement asymptotique. Et ce comportement asymptotique, on va l'obtenir en espérance. Et asymptotiquement, on voit que la pénalité idéale se comporte comme moins 2 sur n, une trace d'une matrice. Alors, trace de matrice, c'est une fonctionnelle de m, si vous voulez. Donc, en gros, déjà, on voit que cette espérance, elle est c'est un grand taux de 1 sur n, si vous voulez. Et plus concrètement, si jamais on le calcule, quand vous prenez un processus gaussien, cette moins de traces, ça devient 2m. 2m, où m, c'est le nombre de paramètres du modèle. Quand vous avez un ARMA, vous avez aussi ça. Alors, qu'est-ce que c'est? Cette espérance, c'est le AIC. C'est le critère AIC qu'on retrouve ici, le critère AIC classique. Mais si jamais on travaille avec un Garch, le coefficient qui est devant n'est plus le même, c'est mu4, qui est le moment d'ordre 4 du bruit, moins 1 fois n. Alors, si le moment d'ordre 4, c'était gaussien, hein, enfin, si le bruit était gaussien, on retrouverait 2 ici. Donc, on retomberait sur nos pattes. Mais en fait, pour un Garch, quand vous n'êtes pas gaussien, quand le bruit blanc n'est pas gaussien, vous avez une autre constante que celle classique pour l'AIC. Donc voilà, donc ce résultat, alors, il nous donne des choses en espérance, ce qui est un bon point, mais on va voir qu'on peut faire mieux en réalité. Alors, justement, on va regarder d'un peu plus près ce qui se passe au niveau du risque et essayer d'obtenir… Oui. 2 minutes?
Oui, bien sûr.
Ah mince. J'ai été sûr que je n'ai pas commencé.
Ah oui, là, je passe 5 minutes.
Mais c'est un enfoiré, j'ai commencé à 10h15.
J'ai dit
Ouais,
respecter les emplois du temps, mais
D'accord. Bon, alors, je termine à toute vitesse alors. Donc, juste pour dire, en gros, quand la pénalité se comporte en grand taux de 1 sur n, ce qui était le cas pour cette espérance de qu'est-ce qui se passe? Le risque sur le paramètre maximisé pour le modèle sélectionné, eh bien, il va être plus petit, il est comment dire, il est borné par le minimum de risque possible, plus quelque chose dans 1 sur n. Voilà ce qui est dit là. Donc, on n'est pas très loin. En termes de risque, on n'est pas très loin du risque optimal. Voilà ce qui est dit, mais ça reste en une constante sur n.
c'est surtout une constante inconnue. C'est pas du tout, il n'y a rien.
Oui, c'est une constante inconnue, oui, tout à fait. Alors, c'est notamment vrai si on prend l'espérance de la pénalité idéale, mais par contre, ça, ce n'est pas vrai si je prends log de n sur n, qui est le BIC. Ah. Donc ça, c'est un premier point. Deuxième point, si on dit que la pénalité, c'est une constante du modèle, enfin une fonction du modèle sur n, ce qu'on a vu jusque-là, déjà, la première chose qu'on voit, c'est que la probabilité de surparamétrer va être positive, strictement. Bon, mais ça, on n'est pas surpris, c'est ce qui se passe pour l'AIC en régression, par exemple. Et en plus, on a un résultat qui est qu'en espérance, mais on voit que l'écart, lui, on a dit qu'il était plus petit qu'une constante divisée par n, mais il est aussi plus grand. Donc, en gros, c'est une constante sur n, l'écart avec le risque minimal. Et donc, ça, c'est vrai à nouveau si on prend ce truc comme le AIC qu'on a, mais ce n'est pas vrai si on prend log de n sur n. Alors, on peut se dire log de n sur n qui est le BIC, ce n'est pas top. Bien, en réalité, on va voir que si. Et donc, si on rajoute une condition ici sur la pénalité, en fait, on voudra qu'elle ne tende pas plus vite vers 0 qu'elle tende vers 0. C'est juste ce qu'on demande. Eh bien, à ce moment-là, on ne va pas sélectionner asymptotiquement de faux modèles. Voilà. Donc ça, c'est un autre résultat qu'on obtient. Donc ça, c'était vrai pour BIC ou pour AIC. Ça, c'est déjà une assurance. On ne va pas sélectionner un faux modèle asymptotiquement. Mais maintenant, voilà le résultat peut-être le plus intéressant. C'est que, bon, alors la condition qui est donnée là, elle est très moche. Mais dites-vous, je prends log de n sur n, c'est-à-dire le BIC, et ça marche. Mais comme on se permet d'avoir des pénalités qui peuvent être data-driven, c'est-à-dire guidées par les données, qui peuvent être des fonctions des données, eh bien, on donne des conditions ici en espérance. Mais ça marche, par exemple, pour log de n sur n, cette condition. Alors, qu'est-ce que ça dit? Eh bien, ça dit que si on a quelque chose comme un log de n sur n, eh bien, asymptotiquement, on retrouve le vrai modèle. Ça, c'est le premier point. Et deuxième point, l'écart avec le risque minimal. On a dit tout à l'heure qu'on n'avait pas une constante sur n, mais on a mieux, en fait. On a un petit taux de 1. C'est-à-dire qu'en gros, l'écart avec le risque minimal, il n'est pas en 1 sur n, il est en petit taux de 1 sur n. Voilà ce qu'on obtient. On l'obtient en proba et on l'obtient en espérance. Et donc, typiquement, pour le BIC, finalement, on fait mieux que le AIC en termes d'efficience. On est plus proche du risque minimal. Ce qui n'est pas classique, d'habitude, mais c'est parce qu'on travaille avec un nombre fini de modèles et avec un vrai modèle sous-jacent, ce qui n'est pas non plus ce que font les gens d'habitude. Bon, voilà. Enfin, dernière chose, en utilisant un développement de la classe, on montre qu'on peut raffiner par rapport à un BIC. Le BIC, c'est, bon, je vous passe un peu les détails, mais on peut aller plus loin et définir une autre pénalisation qui va être d'ailleurs data-driven. Elle va dépendre d'une matrice, ici, log du déterminant d'une matrice. Et ça, c'est en allant plus loin dans le développement de la place qui permet d'obtenir le BIC. Et ça, on montre déjà que ce nouveau critère, il est aussi consistant et il vérifie l'efficience en petit taux de 1 sur n. Mais ce qui va nous intéresser, c'est numériquement ce nouveau critère. Alors, on a fait des essais sur plein de différents processus. Je me dépêche parce que la Paul, il me reste combien? Allez, une minute. Et je vous passe un peu les détails. L'idée, c'est que, en gros, asymptotiquement, on va être avec le BIC où ce nouveau critère, quand n augmente, on arrive à retrouver les vrais modèles. Vous voyez, ça c'est le pourcentage de chances de retrouver le vrai modèle. Et ici, on regarde un petit peu ses propriétés d'efficience. Hein, c'est-à-dire à quel point on est près du risque minimal, et on multiplie par n l'écart pour les deux. Et on voit que pour le BIC, pour ce nouveau critère, effectivement, ça tend vers 0. C'est-à-dire qu'on est bien en petit taux de 1 sur n, alors que pour le AIC, on reste borné. Donc ça, c'était pour une première série de modèles, pour une deuxième série aussi. Et ce qui est aussi intéressant pour nous, c'est que ce nouveau critère, à part pour un modèle, pour tous les autres, on fait mieux que le BIC. Hein, donc on retrouve mieux et on est plus rapide en termes d'efficience. Allez, j'avais commencé par des données de pollution à Marseille. Je termine par elles. Bon, le modèle qu'on choisit, qu'on retient pour ces données de pollution aux particules fines, hein, eh bien, ça va être un ARMA 1,2. Et en plus, on a fait un test d'adéquation après coup qui valide cette hypothèse. Voilà, j'arrête là. Merci bien.
Est-ce qu'il y a une rapide question pour ce passionnant exposé? Mais dans ce cas-là, ah oui.
Tu peux utiliser pour faire un test, pour tester si c'est. Tu peux aussi faire un test, tester si c'est un ARMA. Oui. Alors, c'était en fait le travail précédent qu'avait fait le doctorant Camilla avec nous. On avait commencé plutôt par ça. On avait fait des procédures pour être consistant et après, tu choisis avec une procédure comme le BIC, donc en fait, on peut mettre autre chose. Et après, on faisait un test d'adéquation pour tous ces modèles qu'on a là, qu'on soit Garche, qu'on soit. Et on le fait par rapport, c'est assez classique, c'est un test porte-manteau, mais sur les carrés des résidus. Voilà. Et en le faisant sur les carrés, on y gagne, hein, parce que pour les Garches, sinon tu n'étais pas. Voilà. Donc il faut le faire là-dessus et ça marche. Et même quand on le fait sur le modèle sélectionné, c'est-à-dire que quand il y a le vrai modèle déjà, mais en plus, même sur le modèle sélectionné, on arrive à monter. Ça donne la même chose. On ne perd rien.
So, thank you.
Thank you very
Thank you
much.
for
I
coming.
try to speak English. Okay. So this is a talk about mixture models, and the topic is how to adapt mixture models, and actually deep Gaussian mixture models when data are mixed. This is a joint work with faut cliquer sur quoi?
Sinon, tu appuies sur les...
Ah, ça marche pas ça en fait alors.
Si, ça marche bien.
On focus sur la fenêtre en cliquant avec la suite.
Avec le pad là. Je clique là et maintenant ça y est. Ah ouais, d'accord. This is a joint work with Robin Fuchs. He is a PhD at Marseille, at the Institute of Mathematics, and Cynthia Vironic is a professor at the University of Bologna. The context of is mixed data. Mixed data is when you have continuous and non-continuous data. So this is very classical. You have information features about individual, and you can have here example. I don't know if you can see. Can I zoom the? No. Okay. So here you have the sex or male, female. You have the blood pressure and so on. So you can have variables that are continuous and non-continuous. And such data. Such data are still. Such data are still a challenge when you want to make a clustering. And that's not so easy to cap the dependent structure of mixed data. And then if you can do clustering, you can also understand try to cap the dependent structure. Then you can be able to reconstruct the data. So this is the topic of this talk. We want to model mixed data. Then we want to make clustering, and after to generate such data. And the model is called the deep Gaussian mixture models. This is a recent model that generalized Gaussian mixture models in a few minutes. And what we want to do is to adapt the deep Gaussian mixture model to mixed data, to make clustering, to generate new mixed data. Also, we can use that for to input missing values when you have missing values in mixed data. But I just present these 2 points. Okay, this works well. This also. It doesn't work very well, the invitation, and we have this. This is a work in progress to also to create imbalanced mixed data in regression. Okay. So just to start, what is a classical Gaussian mixture model? What's a Gaussian mixture model? It's just to say you have density, you have a population, but the population is not very homogeneous, and so you have subpopulations. Say n subpopulations, and you assume that this is a mixture of Gaussian. So this is a mixture of Gaussian densities. Okay. So very classical to approximate density when you have different populations. And recently, here are examples of this is a mixture of 2 Gaussians, and you can. This is very clear that you have 2 Gaussian distributions. And here, this is not so easy to see, but you have 2 distributions. Okay. Usually, a mixture of Gaussians is just for a finite number of distributions. And the limit is that you assume that each subpopulation is Gaussian. For instance, you have 2 Gaussians. Okay. And what is proposed by Viroli and McLachlan is to generalize the Gaussian mixture model. So you have first to start with a mixture. Est-ce qu'il y a des trucs blanches?
Non, il n'y a pas de fait.
Il n'y a pas de fait?
Je peux demander aux gens de cette université.
Oui, j'ai un tout petit bout là, j'ai démarré avec le petit bout. Et ensuite j'aurais fait le compliqué. Alors, you start with you have your observation and you assume that your density is not just a Gaussian, but you can have a first Gaussian, a second one, and a third one. Okay. And the idea of Viroli and McLachlan is to say, okay, we do not say that these distributions are Gaussian, but we add another level of mixture, and then this is also a mixture of Gaussian. So this is the idea, we understand. This is not just a mixture of Gaussian, this is a mixture of mixture, and you can continue. Again, 2 or 4, I don't know. And the idea is to construct, to reduce the dimension. At each step, you reduce the dimension. How to reduce the dimension? You use what we call a decomposition formula with what is called a factor loading matrix. So this is the very simple formula. You have your vector y, this is a Gaussian vector, and you can decompose it in another Gaussian vector, but with a smaller dimension. Okay. And you do that. Okay, so you reduce the dimension and you continue. This Gaussian distribution will be also another decomposition of a Gaussian vector in Safran. And you do not use only one decomposition, but you will use as many decompositions that you have of mixture. So if you have three components of the mixture, you will add 3 decompositions in Safran. Thank you. So if we want to write the T, G, and M, so deep Gaussian mixture model, you have your observations. The first step is, okay, you have a first decomposition, but not one, but it depends on the number of mixture. Okay, so with probability P1, P2, P3, and so on. You have your first decomposition, so you have a mixture of Gaussian with a smaller dimension, and you continue. The second variable, the latent variable, is also a decomposition, a mixture of latent variables, and so on. So you have embedded in equations, and you finish with just a vector of Gaussian distribution. So this is the equations of DGNM, so deep Gaussian simulation. So you can see that as a neural network. It could be finally it could be your information, your observations. Then you have, for instance, the 3 components. Okay, so this is a mixture of 3 components, and it could be your first layer, and it would be the 3 neurons of the first layer. And you continue. The second mixture here is the second layer, and you have, say, 2 or 4 components of the mixture that are 4 nodes. So you have a graph like a neural network.
So may I ask you a question of importance? So finally, do you have 3 or 4 neurons?
I don't know. I have to compute with my algorithm. Okay, so I just try to keep the notation. So the first is what is interesting. So you have here the first latent variable. Okay, say Z1. You have still say, okay, maybe I have a first loading matrix that I say lambda 1. This is with probability P1. Okay, but I can have also a second loading matrix, say lambda 2, with probability P2. P3, so I can answer no, P3, yes. Okay, so this is interesting because the important fact is that you have one common latent variable. If you have dimension P here, you have dimension, say, D1, which is smaller than D. Okay, so this is the first step of your DGNM, and after you continue. So you have the second lambda, say lambda 1, 1, 1, lambda 2, 1, lambda 2, 2, and so on. And you have another latent variable, but this latent variable is common. Okay, so the idea is that you do not do that. You do not apply. You have, for instance, freedom, and you do not have a multiplicative. You do not have a multiplicative schema. But you have an additive schema because you can see that your parameters are relative to the same latent variable. What I mean is if you have Z1 here, okay, Z1, you do not have here Z2, Z2 prime, and Z2 and so forth. Okay, it's the same latent variable. So your number of parameters is additive. Okay. Okay, that's what I can to explain. And the advantage of the DGMM is that you have a flexibility of your distributions because you have not a Gaussian distribution for each subpopulation, but you can have a mixture of Gaussian. Okay. The limit, okay, you have conditions to identify the model. I don't speak about it. Okay. What is important is that you assume that given the first latent variable. Yes.
It's a mixture of mixtures, not just a mixture. It's a mixture of mixtures.
Of course, yes, but not a mixture of Gaussian. You see, this is not a mixture of Gaussian. This is a mixture of another distribution. But of course, this is a mixture. But,
oh, it's not a mixture of just one.
This is a mixture, of course, because you can. This is a mixture, of course. But this is not a mixture of Gaussian. This is not Gaussian. This is a mixture of Gaussian. You understand? That's not clear. This is okay. Okay, this is a mixture of 3 components. But this is not Gaussian because this is a gun mixture of Gaussian. Yeah. That's what I mean. Okay, that's why it's more flexible. And you just, if you assume that it's Gaussian, you just do a Gaussian mixture model, of course. Yeah. Now this is just to add a dimension to be more flexible if you want to approximate a new distribution, which is not Gaussian. Okay. And what we want to do,
where is the Gaussian?
For the moment, I don't need Gaussian, but I will need Gaussian to write the expectation maximization exception. Okay, so one important fact is that let's assume that y, so this vector, y is vector, is these components are independent given the first latent variable. So it means that the first step, the first layer, keeps all the dependent structure of your observations. So this is an hypothesis that you have to. Okay, so the limit of DGML it's only for continuous random variable, of course, because Y is a mixture of continuous distribution. So what we want to do is to adapt the DGML to mixed data. Okay. So how to do? There is a way. So this is just to summarize the DGML. When Y is continuous, okay, you have a first step. You have a latent variable which is continuous, and this is a second latent variable, and so on. Okay. Now, if Y is not continuous, what can we do? We just want to merge this non-continuous variable into a continuous space. Okay. So we have different possibilities, and what we use is what is called the GLM for with latent variables, which is a generalized linear model with latent variable. It means that if Y is not continuous, okay, I say that Y given a Z, which Z will be motion or mixture of motion, that's the idea. Y is given Z belongs to an expansion family. Okay. This is a way. This is a way to merge Y into a continuous space. So you have a latent variable, and if Y is not continuous, this is not directly loading matrix that you use, but a transformation depending of the form of your data. If this is 0, 1, you can use a logistic link and so on. Okay. So that's what we do. So if Y is continuous, okay, I can relate Y with the first latent variable, and if Y is not continuous, if it's a component not continuous, I use a transformation with latent variable. Okay, and now we apply this to the DGML. So the idea is very simple. And I think that you see what I do and what we do.
Wait.
White people cannot see you. Okay, so you have your vector of mixed data, and you have a link with a first latent variable. Okay, this is a vector, so okay, and this link depends on the structure of your data. If it's continuous, you can use for the part which is continuous, you can use loading matrix. For a part with binary, you can use a logistic. When it's count, you can use an exponential link and so on. And then you have the first latent variable that you now project in a DGML. So now you continue with the idea of the DGML, okay? Because now this is continuous, so we can use the DGML. That's the idea. So this is exactly the first step. Is not the first step of the DGML, but the only things that we change. But now this first latent variable, which is continuous, is modeled by a DGML. Okay. So let's go. This is the graphic of the MDGML. Y is not necessarily continuous. If it's continuous, finally, this is the DGML. If it's not continuous, you have a first step to get a latent variable which is continuous. Okay. So this is not very easy to make the algorithm. So Robin is a very good calculator. So he made a there is a package on Python. Okay. The first step is very important. This is the initialization of the step, because the idea is okay. You have a dimension D for Y. Which dimension I use for Z? This is a classical, but after for DGML, which dimension I use also? So it's not so easy. Which dimension? So you have constraints for identifiability, but you can first start with say you can mix such. You can use factor analysis, component analysis to try to understand which is the best dimension to start. And after the algorithm will say, okay, the best thing is to start with many components, say, okay, and we use the pruning method. It means that during the algorithm, if this probability is too small, say smaller than the threshold that we fix about the number of dimensions, then we kill this probability. So during the algorithm, you can kill probabilities. Okay? And finally, you have different criteria, but we use we use the criteria that is because we use that for clustering also. So the idea is to say, okay, when I have a kind of a good compromise between inter and intra variability, okay, we form groups, and when so the silhouette coefficient minimize the power distance, which is the compromise between inter and intra variability between group and between intra group. Okay. Okay. So now we can compare this approach to other competitors. Competitors are the following. So this is K-means, K-prototypes, it's close to K-means. Hierarchical clustering. This is the Cohen maps, and this is, I don't remember what is. This is close to the K-means, but this is not K-means, but K-densities, when densities are close. Okay. So we made simulation, and we also compare on 3 famous data sets. Okay, so I don't show you this the result because this is not very important. But I just say that the MDGMM works well. Okay, this is not always the best, but it's very stable. I would say that the best one is maybe for this data set. Okay, it was the hierarchical clustering, but after the MDGMM works very well. Okay, and what is interesting, that you have visual representation of the clustering. So how can you make clustering with such method? You have your data, then you have the first layer. You have 3 components, say for you with the first layer. You have pass. Okay, so this is the pass. Okay, and after you can do here or here. Okay, so you have 2. You can stop here and say, okay, now data from such pass is the first group. You can say that. You can say also, no, I just stop to the first layer and data here are the first group, second group, third group. It depends. Okay, so you can choose which is the best way to stop, and you can have a visual representation. So there is, for instance, here we have only 2 groups. Okay, we stop and we have only two components. Okay, and we force the algorithm because we have 2 components, but which is the dimension? This dimension is, I don't remember for this data set. J'ai du temps encore?
Non, pas du tout, mais vas-y.
J'ai plus de temps déjà?
Non, pas jamais. Normalement, tu as fini pour 5 minutes.
Donc, you have a dimension D, and here you have a dimension D1, which is smaller than D. Just here, I force D1 to be 2, and here to be 3. But I keep 2 components. So you have 2 groups, okay, 2 clusters. And I just want to have a look about if the dimension is 2 or if the dimension is 3. And you can have a representation of your group. You can see if something is more clear here. In dimension 2, this is not very clear. In dimension 3, you can see maybe a more clear separation. J'ai combien de temps pour l'instant?
Normalement, les questions sont finies dans 4 minutes.
C'est pas vrai.
On a commencé il y a 20 minutes.
Oui, non, mais attends.
So, okay, so you can do the converse thing. You can say, okay, I fix here the dimension 2, and I want to see what happens if I fix 2 clusters, or 3 clusters, or 4 clusters. So you have a representation. You have two parameters: the number of clusters and the dimension. Okay. Okay, just to finish, I had ecological applications. If you want. So you can also have a projection on the latent variables to understand which components of y explain or are related to the latent variables, like PCA representation. Okay. So for instance, that was for phytoplankton, and we had two latent variables, two-dimensional latent variables, and we can see why we have such cluster. Here is the depth of the data. Here is the zone. So you have 4 or 5 zones. I don't remember. This is the name of phytoplankton. Okay, and so on. I have another thing to show you, but no. Okay, so if you have 2 groups, the first group is here and the other groups are here. If you have 4 groups, you can see that you have 4 groups here. This is with the zone. Okay, this is a cluster by zone. Just to finish, okay. Just to say that we can use this clustering method to generate data, mixed data. So how to do when you have estimate all your parameters, then you can simulate the latent variables here, and then by a base formula, you now can simulate new variables. Okay. So I simulate Z1, then I simulate Y. And when Y is interesting for me, for instance, well, very okay. This is the algorithm to simulate. Okay. For instance, okay. Up. We study the effect of 2 degrees. We add 2 degrees for the temperature of the sea, and what happens about the what happens about the abundance of phytoplankton? Okay, and we also study the increase of 10% of phosphate in the sea. What happens? Okay, so what we do, we simulate Z1, we return Y when the temperature is +2, and then we keep all the other components, and we see the form of the other components. And when we do that, we can see that this is in blue the true data observed, and in red, or maybe red, what happens if you had 2 degrees in the ocean? And this is the number of phytoplankton. Okay, so you can see it's interesting because you can simulate generate. This is mixed data, and you have maybe the component of the vector is maybe you have 12 or I don't remember the number of data, but you can move data and look at what happens. Data? Okay, let's see.
Is there a question? Maybe God has a question. No. Felix.
How I'm not sure. CGNN model, right? How is it for the current variations of
Yes, okay. Okay. You mean, but what is the link with variational link, or how do you relate the students? I don't relate because we compute then. We compute likelihood, but you could use that's very close. You're right. But we use expectation optimization algorithm. Okay, so we have the conditional distributions, but of course it would be nice to compare. Okay, but I did not try. This is expectation optimization based on the Gaussian assumptions, but you could try such approach.
In variational, I think you expectation optimization.
Yes, but in two sites, no. There is two steps of maximization. Okay, I'm not sure, but okay, it would be nice to have a case.
How data intensive is this? So you need to huge data.
For simulation, it's difficult. Okay, but Robin made a very good job. But if you have just, I don't remember, this is the number of data is just 3,000 or something like that. That's important. So it works with 3,000 observations. It works in a few seconds or minutes, maybe 10 minutes.
So thank you very much. Maybe
Yeah, yeah.
we stop for a quick break. Okay, so Felix, I will let you speak now,
Okay.
and I will try not to interrupt you as the first two speakers. So thank you very much for attending the conference.
Shall I allow myself to remove the mask to talk? And I would like to first thank Paul for the invitation. So what I'm going to present are some results about my work in the Sorbonne University. And this work has been motivated by, so I'm going to present the motivation of this work first, quite briefly, then show that what I want to do is to be able to propose a test, an hypothesis test for the comparison of countries. So I will show what the test, I will show the test that I proposed and some distributional results on the test statistic, and then show some numerical experiments. But first, so this is not motivated by ecology, but epidemiology. We were working with Pierre Boel, with an epidemiologist in Sorbonne University. And this work began like at the beginning of COVID-19. So just after the first wave, we had a ton of data. And this was this new disease that I don't have to present anymore because the whole family of it. But what the epidemiologists didn't know is how the disease behaved and what were the risk factors, how they evolved through time. And we saw, for example, in the first wave, the probability of death decreased a lot. Like in the beginning of April, I think that something like 20% mortality for the first week, and then it decreased to below 5% at the end of the first wave. And what the epidemiologists were interested in is to be able to find out the risk factors, as in every other disease, but be able to quite rapidly understand how the risk factors impacted the risk of death to be able to adapt the care of the patients that come to the hospital. So what I have is some kind of data set where the data set from the hospitals of APHP, the Assistance Publique Hôpitaux de Paris. So all the hospitals in Paris, they record all the patients for which there was diagnosis of COVID-19, either from PCR analysis or from radio, an X-ray. Okay, and the data that I have here is something like this, where I know when the patient came into the hospital, I know when they left the hospital and whether they left alive or dead. So sorry for this, for the macabre characteristic of this data set. And some characteristics, some simple characteristics, and what they wanted to, and so to summarize what they wanted to know, they wanted to identify the risk factors of the disease, to identify the groups at risk, so that they can say, okay, this person is an old person with hypertension. We have to put it in an intensive care unit right now, and to determine how they evolved through the pandemic, and to be able to compare basically populations from different time periods. Okay, and so statistically speaking, I put myself in the context of supervised learning, where what I want to know is if I have two independent samples. Okay, so for example, one sample from the beginning of the first wave of the pandemic and one sample from the end of the last wave of the pandemic. So just some notation I will be using afterwards. I call the two samples X and Y, X and Y, okay, but each Xi or each Yj is a doublet UV of input. So U is the input, so it's the covariates, the age, the sex, the hypertension of the patient, and V is the outcome. So it's a binary outcome. It's either he left the hospital dead or alive. Okay, and I assume that the distribution, the distribution function of X and Y can be different. Okay, and so what I want is, for example, so here given two covariates, okay, U1 and U2, and the outcome, which is binary outcome 1 or 0, so blue or red. what I want to be able to do is, first of all, find out what is the probability of death of a given group of people. Okay. And second, I want to be able to compare the probability of death in the two groups, in the same group, in the same arbitrary group of people. Okay. But what I have is that potentially the distribution of the covariates U are different in the two data sets. Okay, so for example, at the beginning of the first wave, there were a lot of old people of young people in the ICU, and then at the end of the first wave, pretty much all the young people were taken care of, and only old people were left in the hospital. Okay. And so what I want to have is some kind of test saying whether the conditional expectation of the outcome given the input here is the same in the two data sets. Okay, so this is what I want to find out. Okay, whether the two conditional expectations are the same, or since I am in the classification case, whether the conditional probability of the outcome are the same. Okay, and the model that we settled on to actually, the first step is to be able to estimate this kind of values. Okay, so what we decided on is to use trees, okay? Decision trees. So we split the sample space into a partition with our tree, and then the tree just gives us the prediction. So the probability in each leaf of dying. Okay. And so why did we use trees? It's because my supervisor at the time was really interested in using trees. And then another thing is that for actually medical doctors, trees are nice models because they're really easy to interpret and understand. Because it's quite easy. If say you have a patient that is arriving in the hospital, you can just check whether they are, for example, above 75 or not, and if they're not above 75, do they have comorbidities or not, etc. So it's easy for them to be able to adapt the care of patient with a decision. So really rapidly, I recall what the CART algorithm is. So the CART algorithm is maybe the most famous algorithm to build decision trees. Okay, it has been introduced 40 years ago. And basically, you have a sample space that you are going to split recursively along one of the covariates. Okay, so and the split is chosen in order to reduce the impurity in each subcells. So, for example, here we want to sample this. We want to partition the sample space such that all the blue dots are in the same cells and all the red dots are in the same cells. So the first thing we want to do, we see that cutting something here, we are going to leave all the red cells below and then the blue cells above. And then we see that another cut here is a nice way to partition the sample space. Okay, and that's how we build our CAT tree. And then we stop when we achieve some kind of stopping criterion. So for example, whenever we have too few observations in a cell, or whenever the impurity does not reduce anymore, something like this. Okay. So this is the algorithm I'm working with, the well-known CAT tree, and this links to what I said about why CAT trees are nice for application is that they are really interpretable. They can handle missing data, and we have a lot of missing data in our database, so it's nice. And however, establishing theoretical properties for CAT tree is really difficult because we have to take into account the recursive construction of the tree, and so we have really few theoretical properties. The most important being the one that was given by Pommeret himself, which is the L2 consistency of the CAT tree. So asymptotically speaking, the regression function is well estimated in an L2 sense by the CAT tree. And then 30 years later, we had to wait 30 years to get some theoretical results in a non-asymptotic framework. And usually the results are more empirical. And for example, in the last decade, there has been a lot of work on working with how do we find the variance of the prediction of the trees, and it's purely empirical by by proposing some estimators and true simulations, seeing that they behave well, pretty much. So if I if I come back to my problem, I want to be able to compare the trees, but I'm not going to look at the structures of the trees. The structure of the tree are really sensitive to perturbation in the learning set. So I'm not going to look at the structures of the tree, which is how the partition has been cut, but only looking at the partition at the end, and so looking at the leaves of the tree and pretty much looking at the prediction of the tree. So I want to be able, okay, are the prediction of this tree similar to the prediction of these trees? Okay. And if I come back to the framework that I gave a little bit earlier, so I have my two trees, and I want to say, okay, are the conditional probability function in the two data sets the same? Okay. So what I'm going to give myself is a few test points. Okay. So these test points tell me, okay, I want to test the equality of the conditional probability function, but in this area. So I'm going to give myself a few test points in this area, or a testing distribution equivalency. Okay. And then over these test points, I'm going to compute what I'm going to call the similarity between the tree number 1 and the tree number 2. Okay, and the similarity is just going to, I'm going to look at the prediction of the first tree on all the UIs, the prediction on the second tree of all the UIs, and I'm going to look at a distance d between the prediction of the first tree and the prediction of the second tree, and that over all the test points that I've given myself. So I'm calling this test statistic h of xy, where x and y are the samples. You'll see why I'm taking this notation in I think one slide. And the null hypothesis that I'm working on is whether, and the one that I want to be able to reject or conserve, is whether the conditional probability function, the conditional probability of the outcome given the input is the same in the two data sets. Okay, and so the question that I have now to ask myself is, what is the distribution function of this test statistic? Because I need it to be able to create the rejection set and to say whether I can reject safely my null hypothesis or not. But as I told you a little bit earlier, it's really difficult to establish theoretical results on trees, and even more difficult to establish distributional results. And so I tried for a few months to find something on this. I failed consistently. And then I fell upon an article, which was an article by Mensch and Hooker, and then Mensch and some other colleagues extended their results. Well, basically they're saying, okay, you have, if I translate this article in my framework, rather than building here my statistic on the tree built on the whole sample X and the whole sample Y, what if I looked at my statistic built on subsamples of my two data sets? So recall that here my samples X and Y are of size M and N. What I'm going to look at is so trees built on a subsample of size R of X and a subsample of size S of Y. And if I do that a lot, if I take all the possible subsamples of size R and S of M and N, I can just look at the average of all these subsamples. And what I have there is actually a U statistic. So a short reminder on U statistic. What is a U statistic? And I will come back to this slide afterwards. This was studied about 70 years ago as an extension of the mean to dependent variables. And the idea is that rather than looking at the average of a function of one argument, for which we know the central limit theorem, which gives us the asymptotic normality, we're going to look at the average of a function of multiple arguments, okay, up to R arguments. And the idea is just to look at the average of the, given a sample of size N, we're going to compute all the subsamples of size R, okay, we're going to average the function h, the kernel h, and all subsamples of size r. And this is a use statistic. The thing that is complicated compared to the standard CLT is that you have dependence between the different variables, since you have some repetition of the xi through the sum. Okay, and you have a few famous use statistics are some like the variance. The variance can be written as a use statistic or the man-Whitney statistic. And the idea is just by projecting the use statistic on the space of functions of only one arguments. Okay, so we're going to project on the space of function written as a sum of only one arguments, and we can easily show that the use statistic is close to its projection, and then since a function of this a function like this is just a sum of independent variables, we have a CLT for that, and since the use statistic is close to this simple statistic, we can write a CLT for it. Okay, so that's the usual central limit theorem for use statistics of one sample. Okay, it's quite easy to show. We just have to project and show that it has asymptotically the same variance. Okay. So coming back to this case, what can be changed? What is a little bit different is that we have two samples rather than one. But another thing that is a little bit more complicated is that we're going to build trees on subsamples of size R and S, and we want that asymptotically speaking, R and S goes to infinity. Okay, when the samples X and Y grows in size, we also want our trees to grow in size. We don't want our trees to be fixed with size R and S. So we have to work in a framework where not only M and N are going to infinity, but R and S are going to infinity as well. Okay. And another thing is that, practically speaking, whenever M, N, R, and S are large, the number of subsamples that we have is extreme, and we can't hope to compute this whole complete use statistic. So we are actually working with an incomplete use statistic where we're going to choose a finite number of subsamples that we choose even to equal to n, big N. And we have to choose big N such that this use statistic has good convergence properties. Okay. So this is where I'm standing right now. I have a test statistic, I have a test statistic that I can write as an incomplete use statistic of infinite order, where R and S are allowed to go to infinity. And it turns out that by following the same methodology that they use in Peng, Coleman, and Hedge, but extended it to two samples, we can easily find an asymptotic distribution on this incomplete use statistic. So I pass all the details, but basically, by making some assumption on the rate of convergence of the of all the R, M, S, M, and N, also all the let's call them hyperparameters. So saying that basically the original sample X and Y goes in size in relative size, so they are basically of the same size, and that R and S are really they grow in size, but are negligible compared to M and N. Okay? And in this case, assuming that the number of subsamples that we choose for the incomplete, the number of
Non, bon, d'accord, formidable. Présentation. Ah.
Tu t'énerves pour rien.
Mais bien sûr que je m'énerve, c'est un Mac.
Ne t'énerve pas. Attends, ne t'énerve pas, il ne faut pas s'énerver.
Activer le mode plein écran.
Voilà. Et ça va aller.
Moi, je vais juste enlever cette proportion dégueulasse qui est l'éléphant.
Celui-là, tu l'as mis.
Ah, je l'ai pas mis.
Ah
Il
non,
est
mais
apparu.
Attends, admettre. Écoute, je ne sais pas. Ah oui, d'accord. Super. Ouais,
Ok.
super. Bon, écoute, non, peut-être pas. Parce que tu vas le laisser, de proportion. Tu vas le laisser.
Non, mais il y a. Bon.
Je ne sais pas si c'est.
Mais regarde, ça, c'est du Mac. Ça, c'est du Mac. On va faire
Ah.
continuer. Et on va faire OK, merci Mac. Donc, il n'y a rien qui fonctionne.
Non, qu'est-ce que tu me fais?
T'inquiète pas. Bon, on a une proportion qui a
Très
pas mis
joli.
l'écran. Je suis désolé pour la proportion.
This is an addition to the top.
So by assuming this rate of convergence of all the hyperparameters with respect to n and m, we can find an asymptotic distribution for our use statistic. Okay? And here, what is actually, this is really a simple version of this convergence, where here I don't allow the number of subsample n of the complete statistic to be too large. And actually, when I do that, the normality, the asymptotic normality of my use statistic is ensured by the fact that I'm drawing a very small amount of subsamples, and is given basically by the multinomial here that I have. But if I allow myself to draw more subsamples than this little O of n over s, then I have to assume some more, I have to make more assumption on the way that the complete use statistic here. Let me rephrase that. What I'm using here is that I'm not using at any point the convergence of the complete use statistic. The asymptotic normality is ensured by the fact that I'm not drawing too many subsamples. If I want to draw more subsamples, then I have to ensure the asymptotic normality of the complete use statistic, and then I have to make more assumption of the kernel H. Okay. And basically, this is quite nice because I don't need many assumptions, only an assumption on the moment of my kernel H. But here in my problem, I have a problem of classification where the outcome is 0 or 1. So the kernel is basically bounded by 1. So I know that my assumption of moments is correct. Okay. And then some other thing that this kind of methodology can give, which is not related directly to the test statistic, is that basically by relating, we can look at the p order quantile of this functional H. By relating to the result of new statistics, we can actually find on CLTs on the sample p quantile of H. So we can get some kind of distributional results for the prediction of the tree itself. So this is something that is, let's say, quite new because we didn't have up to this point any thing. So it's not related to the statistic, but it's quite nice that we were able to say something about the prediction of the tree itself. Okay. So now I have an asymptotic distribution for the test statistic under the null hypothesis. What I'm missing is that these two parameters that appear here, which are theta rs is just the expected value of my kernel, and zeta rs is the variance of my kernel, I actually do not know them in the null hypothesis. Okay? So I have at one point to be able to estimate them from my original sample. And there, the idea is to use a bootstrap approximation of my sample, okay, to be able to compute it. And it's actually a mix between a subsample plus a parametric bootstrap approximation, where basically under the null, I'm going to say that the two samples are the same. So I'm going to compute the average prediction between the first tree and the second tree for all u. And then I'm going to generate some bootstrap trees, okay, of size R and S, since I need trees of size R and S to get the estimators of these parameters. And then for this, I just subsample the inputs, and then the outputs, I draw them according to a Bernoulli with probability given by the average probability between the two trees. So this is some kind of parametric bootstrap to actually get some subsamples as if I was under H2O. And then I can build some trees on this bootstrap statistic, and then estimate my two parameters. So now I have all the components. I have a statistic. I have its asymptotic distribution of the null, and I have some way to estimate the parameters that appear in the test statistic. And so I can look at the test statistic and look at some numerical experiments to see whether what I propose is actually gives correct results in a non-asymptotic framework, obviously. So what I created is a simple numerical experiments, some simple simulations where I basically generate data using a very simple GLM model. So I simulate two simple covariates, U1 and U2. The first one, U1, is just some kind of mixture of Gaussian. Okay, so which can be, for example, if I relate these to my original motivation is just the age of the patient that comes to the hospital. A second variable which is discrete, which is, for example, the gender of the individual. So, and then the outcome is generated via a logistic model, okay, with some parameters that are chosen such that my simulations are close to what I observe in the original data set. And what I'm going to look at several scenarios. First one, I'm going to test whether under H0 my hypothesis test behaves correctly. And one thing that I didn't talk about is how I choose the test points. Right now it's purely arbitrarily. So I'm going to look at the case where the test points are generated under the same distribution than the data set that I'm using. I'm going to look at another case where the test points are generated from another distribution. So for example, here I'm only going to test basically old people, so people under this Gaussian. So I'm going to test the similarity between the two trees only for old people. And then I'm going to work under alternative scenarios, one for which one of the sample is generated with a higher risk for age, and one where the second sample is generated with a higher risk for people being male. And one thing that I still hid is that at one point I have to choose a distance with which to compare the two predictions. Actually, the distance that I use should not have any impact asymptotically speaking, since I showed in the theorem that we don't need any other assumption on this distance other than the moments of h to the order 6 are bounded. Okay, so since here my outcomes are bounded by 1, I can take any distance basically, and this will fulfill the conditions. And so, see, I tested a few distances, like quadratic distances and absolute difference between the two probabilities, because this can be related to the L2 consistency of trees. So these distances are quite natural. But here, since I'm in a binary classification framework, I'm going also to look at some kind of cross entropy between the probabilities predicted by the first tree and the probability predicted by the second tree. And another thing that I'm going to look at is, rather than suggesting something that is a sum of distances between the prediction, I'm just going to look at the maximum of the difference of the absolute difference in prediction. So this is some kind of Kolmogorov-Smirnov statistic, where I'm just looking at the maximum difference in prediction between the two trees. And so under H0, so I'm simulating a data set of size 1000, and then the subsample trees are created with size 50, and I'm taking only 50 trees to build my U statistic. What I plotted here is the result over 100 simulations of the p-value of the test. And if I'm under H0, the p-value of the test should be distributed as a uniform 0,1 random variable. And so in black is the empirical cumulative distribution function of the p-value of the test. Okay, and then in gray are the different confidence intervals. So in dark gray is the confidence interval that is obtained through a standard TCL. And it is a pointwise confidence interval, and the light gray is the confidence interval obtained from the I always forgot the name, the DKW inequality. So Vorer Wolfowitz inequality, that is, in which the thing that is nice is that this light gray confidence interval is a simultaneous confidence interval. So it should hold the fact that the whole black curve is included in the light gray interval should hold with probability at least at worst 95%. Okay. And so we see that under each row, so the two data sets are the same, and the test points are simulated from the same distribution function than the data sets. We have something under each row that is the p-values are distributed as uniform 0, 1. So I'm quite okay with this result because this was what I expected, and this is for all the distances that I've been looking at. And then if I change my test points so that my test points are only on a subset of the samples here, so on the subset of all people in my estimation, I see that under H, I still find some p-value distributed as a uniform 0, 1. So my test in these limited simulations, my test under H0 holds. So this was a nice thing. And then looking at other scenarios, so for example, above is the scenario where I increase the mortality of older people in one of the data sets, and I see that I reject the null hypothesis in about 60% of the case for this kind of choice. So I do detect some kind of difference between the two data sets in the majority of the case, and then here the same thing, but when I change the parameter for mortality for men, and it's a very less sensitive, but still. So a lot of things here there are a lot of things that I have not done in this simulation. One thing would be to see how the power of the test changes when I change the parameter big N and little r and little s. So should I go more subtrees, or should I build larger subtrees or not? So this is a work in progress where I would like to at least empirically find out what is the correct choice of big N and R and S. Okay. But then I have not done this. And just as a proof of concept of how this could be applied to the data that I have, so I don't have a nice application because the original motivation with the data about COVID-19, we had an original data set that was quite poor in covariance, and we were unsure that we would get the real data set at one point. It's been 1.5 years, and the data set is not here yet. So this is just on the really poor data set that we had at the beginning of the project. And basically what I did here is that for each week of the first wave, so this was March and April of 2020, okay, I build a tree for each week, so on completely independent data, where I'm looking at the mortality of the patients. And what I'm doing is that the beginning of March was the week with the highest rate of mortality. And what I'm looking is each other week, I'm going to compare it with the first week, only for all people. So what I'm looking at is whether at one point there is a difference in the mortality of all people in the first wave. And so obviously there are some things that should be corrected here regarding to multiple testing, but here I have just reported the p-values of the tests, okay? And we see that it took something like 1.5 months for the mortality for all people to be different compared to the first week. So we actually got something where we saw a decrease in mortality in the first wave, but this was more associated with the fact that there were young people appearing in the hospital, which didn't die a lot, rather than the fact that the mortality in all people was decreased through better care and through better treatment. Okay? It took really 1 month and a half before we saw any change here. Another thing we could do is, for example, I checked the mortality in the 3 first waves of the pandemics. Okay, for example, looking only at young people and looking only at older people, and here it's older people with comorbidities. So people with either hypertension, diabetes, or obesity. Okay, and you can see that for young people, we didn't see any real change in mortality, and the p-value of the test comparing the mortality of one wave to the previous one did not reject the hypothesis that the mortality is the same in those people. And for all people, we see that there was a betterment between the first and the second wave. So a betterment, is it the virus that was less lethal or the treatment that was better? I can't say for sure, but well, we can say something. So this is just a proof of concept of what could be done if you had some better data. So in a summary, what is nice is that we were able to propose a test comparing the conditional expectations between 2 samples. That we decided to work with 3, but actually there is nothing that says that it works only for 3. It works for any kind of regression function that satisfies the condition of the asymptotic normality of the U-statistic. And it could be extended to other models, but also to other unsampled methods. So, for example, random forest, tagging, etc. And we get some nice distributional results for the subtrees. The trees built on subsamples. But there are still some things that I want to look at. Is first of all, at one point, I have to estimate the parameters here that appear in the asymptotic normality, and here it's purely empirically, but I would like to show that the bootstrap approximation actually holds true. So this is a work in progress. And the other thing is that up to now, the test points were chosen completely arbitrarily to be able to look at only, for example, old people, young people, etc. I would like to, for a given alternative hypothesis, find out if there is a way to select the best test points so that the test is most powerful compared to other tests. And then one day we can hope to use the full data set to actually say something. I thank you for your attention, and if you have any questions.
Any questions? Are there any questions?
I guess you kind of answered that here, but so the only assumption that you need from your model is this the normality?
Yes. So the only assumption in this, let's say, simplified version of the theorem is the boundedness of the kernel. But actually, here the rate of convergence is actually really low. If we want to improve the rate of convergence, we have to increase the number of subsamples that we use to build the U-statistic. But when we increase the number of samples that we use, so this variance decreases, but then it becomes comparable to the variance of the U-statistic, of the complete U-statistic itself. And so we need some condition on the complete U-statistic, because its variance is going to be comparable to this one that appears here. And then we need some more conditions on the kernel. In particular, it gives us a condition on how S and R are allowed to go to infinity with respect to M and N. Pretty much they can't grow too fast to infinity. They have to go really slow, whereas in this result they can go almost as fast as they want, as long as they are negligible.
And is that the reason why you focused your analysis on cartridges? For those who have this?
No, actually for cartridges we don't really have we don't know if it actually fulfills the condition for the convergence of a complete U-statistic. So this would be a reason not to use cartridges, to be honest.
So thank you again. So the proportion is good. Okay, so let's just suspend a bit the. Okay, thank you, Arnaud, to give the last talk. I don't know if people can see well on the blackboard, but can you speak? I don't hear you.
Yeah, I can speak,
Okay.
no problem.
Okay, good. So you are welcome, and unfortunately you couldn't attend, but anyway, there is this virus everywhere also. Okay, so thank you for coming.
Okay, so thank you all. I'm going to present a work entitled Stochastic Control of Ecological Networks. This is a joint work. I'm sorry, there's a cat and it's a little bit annoying. This is a joint work with Angela Gurtu from the Indian Institute of Science. So basically, to give you the context, land use changes have led to the ecological fragmentation of territories and habitats, which provoked the erosion of the biodiversity and the intensification of pressures on the natural environment. The European public policies have emphasized the need to ensure interconnectivity through the establishment of ecological networks between natural reserves. For example, the French Environment Roundtable Act has been voted, and it stresses that the protection of biodiversity and ecosystems should be undertaken by means of green belt networks. So in practical terms, this took the form of supplying biodiversity hotspots and forest green corridors. Those are meant to facilitate the adaptation of vulnerable species to local or broader environmental disturbances. However, the implementation of ecological networks in forest ecosystems must not prevent the foresters from exploiting the timber stands, for their multifunctionality is about both providing good products as it is about protecting the ecosystem services. For the control devices put in service to provide an ecological network are restrictions in cuts to parts of the forest, the establishment of a number of dead trees with the aim to create senescence isolates, or the performance of forestry work undertaken to ensure some optimal forest cover in the woods. So the question that we try to address in this work is, what does it take to preserve the connectivity of an engineered ecological network in uncertainty? The topic of connectivity preservation, once the network has been put in place, has rather been neglected. Most of the literature proposes a framework where the nodes choose to form or maintain links at a certain cost. Contrary to the existing papers, which model a budget-constrained optimization in the design of optimal corridors, we turn toward a connectivity-constrained optimization. Corridors have to be implemented by taking the precaution of verifying that their number and sizes are functional. And rather than the maximization of discounted expected payoffs of social planners, heightens our curiosity is the capacity of forest managers to provide a stable ecological network in uncertainty. So some studies consider the opportunity costs to optimize the spatial distribution of conservation measures. Instead, we wish to size the financial resources needed to preserve the network connectivity along. Increasing uncertainty puts it at greater risk of rollback. So the aim of the following work is to model the maintenance of ecological networks in forest environments built from bioreserve patches and corridors, when these grids are subject to random processes such as extreme natural events. The management plan consists in both providing temporary and sustainable habitats to migratory species. It also aims at ensuring connectivity between the natural areas without any interruption. So after presenting the random graph theoretic framework, we applied stochastic optimal control to the graph dynamics. Our results show that the preservation of the network architecture cannot be achieved under stochastic control over the entire duration. it can only be accomplished at the cost of sacrificing the links between the patches by increasing usage of the control devices. Now, this would have a negative effect on the species migration by causing congestion among the channels which are left at their disposal. And the optimal scenario in which the shadow price is at its lowest and all connections are well preserved occurs at half of the course, being the only optimal stopping moment found on stochastic optimal trajectories. This means that the optimal forestry policy has to cut down the timing of the practices devoted to biodiversity protection by half. Consider an ecological network built from the ecological areas and corridors. The grid is based on the Euclidean metric defined on dimension R. The link formation of forest managers is contingent on engineered distances between the network constituents. Their purpose is to enable living species to migrate from an area to another. They are allowed to move in all directions, such that the network is an undirected graph G. The graph consists of vertices capital D, where I and J give indication of two randomly chosen areas. Nodes can either be intermediary patches or bioreserves, the second being the targeted areas in which the migration ends. In ecological networks, the targeted nodes represent the bioreserves, the aim of which is to accommodate the species in process of migration. And unmarked nodes stand for the patches which temporarily host the species heading toward bioreserves. We differentiate between the two for the upcoming optimal control formulation. In short, consider the set of edges capital E composed on n-dimensional vectors at time t. So after what preceded, capital X is the vector of n edges between patches at time t, and capital Y is the vector of n edges between bioreserves and patches. Both E and J vary infinite time for t between 0 and capital T. Now consider capital A to be an adjacency matrix with non-negative elements Aij, and assume that Ij belonging to capital E, implying that two nodes separated by a proper distance are purposely connected if and only if Aij is strictly positive. Finally, assume the existence of a convex hull of vertices omega at initial time step 0 as an n simplex with the Euclidean norm in R. So the convex hull is a mathematical notation for both the existence and the maintenance of the structural network architecture. So the following figure is a simplified illustration of a forest environment formed of 5 vertices and 6 edges. The ecological network built within the forest connects, for example, nodes I, J, and K, and O at time t equals 0. Node O represents the final destination, that is, a bioreserve that migratory species are supposed to reach through patches I, K, and J. The graph is composed of patch-patch connections, such as XIK, and of one bioreserve patch connection, such as YJO. Since the distances between L and A or L and J are too long, it can be noticed that from the start, forest managers exclude both area L and its connections from the grid. This is because migratory species have limited capacity of displacement, which cuts some nodes from the system of connections. So from the foregoing, a successful management plan is to keep the identical topological configuration at both starting time t equals 0 and final time t equal capital T. That is, for some t between 0 and capital T, we have omega 0 equal to the expected omega at capital T. So by reason of the stochastic processes governing natural events, The implementation of green corridors on random graphs is more suitable. So we are in presence of random graph G. It is defined with respect to the probability measure rho. The dynamic graph then evolves into a graph valued random variable. So one observes in the following figure that omega 0 is not equal to the expected omega at capital T. In this case, the randomized convex hull includes only nodes I and K. As a consequence, the migration toward bioreserve O through patch J is found to be defective at T equal capital T. And because in expectation, XJO and is no longer operational and node O is deleted from the ecological network, the updated grid is considered to be disintegrated. So continuous dynamics of the vectors of edges D capital X, D capital Y, which belong to the domain D, are considered to obey the etostochastic differential equations. They're in the following form. So the respective equations describe the probability distributions for the disturbances between patches and between bioreserves and patches to be at a given level at a given time, while capital X represents an n-dimensional vector subjected to time-evolving stochastic processes. W reflects the local Brownian motion as an n-dimensional linear continuous time stochastic process. Now, Brownian motion makes it possible to compute the probability of change in any direction during a certain time interval. As for vector B, it typifies a diffusion process with local drift. It exemplifies the change in distance, initially meant to ensure the migration of species between two nodes. The control vector UX, which belongs to set capital U, I apologize, provides information on the use of the silvicultural control devices to preserve the ecological network. The first term is defined as the benefits at period T of controlling distances capital X at rate UX. B represents the management policy of facilitating migration to bioreserves whenever the initial vertex the population of migratory species finds itself in. And the local volatility or standard deviation rate is represented by its diffuse tensor profile through positive definite matrix L. Now, the diffusion is the variance in the rate of change in a unit interval, which means that diffusion gives indication on the dispersion of the probability distribution. Now, this volatility generates fluctuations in distances, which in proper sequence causes the use of control devices to fluctuate just as much. So what the stochastic differential equation tells us is that in a small time interval, the variations in capital X are an amount distributed with expectation E and variance capital L. So to produce the control law, the application of collaborative devices to the task of all types of edges assembling necessitates to exert the joint torque control. The dynamics make the overall control hard to implement, so that the joint torque controller with dynamic responses is necessary. The differentiated connections between the patches and between bioreserves and patches are hence converted through dynamic control vectors through a single resultant to joint control torque vector. The torque being additive, it represents a net joint control where the devices sum up into a common vector UZ. Now we observe that we have UZ instead of UX and UY. So we have to estimate the torque distribution as follows. The probability density function of random distances capital X and capital Y which is rho, progresses according to the parabolic partial differential Fokker-Planck equation of order 2. The use of the Fokker-Planck equations enables us to study the Brownian motion when the initial probability distributions are unknown. The time evolution of the probability density function under control devices is apprehended through the following time derivative. So the second part of the equation takes the form of differential operator capital F. And the goal is to obtain, by revising the rates of control, the average property of motion. So we assume the behavior of a system, the state of which is at any instant of time is characterized by distances capital X and capital Y. It is assumed that the system can be controlled. The system is equipped with controllers, the position of which dictates its future evolution. And these controllers are characterized by points UZ, which are the control variables. Now, stochastic optimal control minimizes the cost of control along the entire time path. Its purpose is to preserve the ecological network at the lowest possible cost. Preserving the ecological network means that all random edges allowing for species migration remain intact throughout time. So by starting with the terminal time step and by ending with the initial one, we solve the optimization program backwards in time. The following performance function ensues, so capital J. So the expected final cost is situated in the first term. Its form is an inner product that considers weighting function phi. The latter incarnates the distribution of shadow prices for achieving desired migration through stochastic joint optimal control UZ. The inner product is discounted at constant rate R at time capital T. The second term of the performance function collects all expected costs discounted at rate R under control UZ. Integrating over time permits obtaining the present value of continuous flow of costs. And the performance function, the dependence of which comes from exponential discounting, is a two-dimensional convection diffusion equation. So the optimal control problem becomes the minimization of the performance function with respect to the cost of control, subject to the dynamics of joint distances. So put differently, we have the minimization of the performance function subject to dz, which is equivalent to dx plus dy. The solution to the problem consists in finding an open loop control sequence UZ, the latter being dependent on the cost recorded in the final state and on the costs integrated over finite time. It reaches minimal cost of control when it is operational. The optimal control is also a penalty to any deviation from this level of cost. The necessary condition for desired controllability is that UZ star minimizes the Hamiltonian for some t between 0 and capital T. We have the following expression of the Hamiltonian. So through the solutions of partial differential equations, the Hamiltonian covers integral terms. Probability density function rho is displayed in the first system. The joint distribution evolution in capital F prime, with F prime being the adjoint operator of capital F, satisfies the Green's identity. In other words, the linear operator equivalently acts on the boundary of capital D. As such, the region under the differential operator is bounded, and the convex hull is preserved from randomly growing ad infinitum. As for pi, it represents in the form of a Lagrange multiplier the optimal control constant or the shadow price. So the Hamiltonian can be solved through the standard first order optimality condition by computing the partial derivative of the Hamiltonian with respect to UZ. To put another way, we have the following derivative with respect to UZ. So the minimized Hamiltonian is convex both in capital X and capital Y. The necessary and sufficient condition for the minimization of the Hamiltonian is met. Such a property comes from the Arrow-Mangasarian condition, which shows that if in presence of continuous first partial derivatives with respect to uz, capital H is continuous and convex in uz, then the Hamiltonian is minimized. And the control sequence uz is denoted as the global minimizer of the function. Now, because rho cannot be identified, the inner product shall be computed by means of the derivative of the joint distribution. As a consequence of the Kolmogorov backward equation applied to continuous time Markov processes, the Feynman-Catch formula can be borrowed. The dynamics becomes the following time derivative of the shadow price, and this negative sign discloses the willingness to pay to ensure connectivity of the ecological grid. The differential operator is bounded by the equality such that phi z at capital T is equal to phi z at capital T, where phi z at capital T is the terminal condition at terminal time step capital T. And provided that rho z generates from the linearity of the inner product the expected value of phi, the optimal control yields the expected joint distribution of shadow prices. So as a result, we have the following optimal level of the shadow price, phi star. The optimization has to be well defined. In parallel, the integral has to converge. So we are in attendance of a transversability condition where the limit of x0 when t tends to capital T is equal to 0. In summary, we have a pi star, which is equal to phi z at capital T whenever t tends to capital T. Now, this result reveals the presence of real option evaluation, in which an optional investment on natural resources dependent on the cost to be incurred for the resource preservation takes place. Real options are to be seen as the willingness of forest owners or managers, but not the obligation to undertake at a certain cost the stabilization of the ecological network, the state of which is governed by random processes for an additional unit of time. We finally have to virtually decompose the joint torque by projecting the control onto the height weight. Now, in an unavoidable fixed budget constraint driven by the cost of control, the control of the kth parameter adaptation is designed as the following expression. Now we have KUZ, which is between 0 and 1, and it represents the weight assigned to an isolated control, the remainder being given to other joints under scrutiny. Our last objective is to derive results in the context of a dynamic programming problem on the stopping moment, which has to be optimal, of course. After having found through the formulation of an adjoint problem, an admissible control device leading to an optimal trajectory of the random graph, we aim at revealing the optimal stopping times. Indeed, theoretical optimal trajectories can sometimes be synchronized from the real context forest management. This is particularly true in that forestry is practiced with respect to very long management plans. For example, the rotation in forestry going from planting to harvesting can reach a length of action up to 100 years. The dynamic programming approach involves breaking the problem into a sequence of small moment decisions. We thus denote tau, the collection of topic moments, and we then define a sequence of value functions capital V. It incarnates the implementation of the optimal policy throughout the sequence. So the optimal stopping problem is defined as the following criterion. So provided uz tau is equal to uz t, stopping time tau becomes an optimal rule if sequence capital V yields simultaneously at moment tau star the minimum of performance function capital J at time t. So looking at it more closely, it appears that the solution to the last stopping moment has already been formulated through the Feynman-Catch type equation. We now look at the derivative of pi with respect to tau. And provided that the optimal forestry policy depends on the optimal timing sequence, the shadow price or the adjoint variable can be assimilated with the temporary minimum willingness to pay for a forest manager to dedicate to the protection of biodiversity. In other terms, we have the expected omega at tau star, which belongs to domain D and U. And the risk of ecological network dismantling is minimized, which we summarize in the following proposition. The preservation of the ecological network in uncertainty is undertaken under stochastic control through stochastic shadow pricing. The latter permits safeguarding the configuration of network connectivity. In that case, the adjoint-based optimization becomes the time-evolving willingness to control. Ultimately, the adjoint variable distribution unveils, along the optimal timing sequence, the stochastic value of the network connectivity. So I will now shortly present some simulations. So we reduce the control to two vectors, capital X equal to X1 and capital Y equals to Y1, with X1 and Y1 being two corridors subject to random variations. The nonlinear dynamics match with their evolution in uncertainty. So the time evolution of distances between the patches is a function of time, the distances between bioreserves and patches, and of the inverse cumulative distribution of the standard normal distribution. Equally, the time evolution of distances between bioreserves and patches is a function of time, the distance between the patches, and of the inverse cumulative distribution of the normal distribution. The fact that both types of evolution depend on complementary distances reveals that the migration objective depends on the sum of both types of edges. This property provides evidence for the cascade effect in natural environments, whereby a change is proportional to the nonce number of interactions. And in this applied version of the stochastic differential equations, we emphasize the fact that the ecological network needs to be connected despite the random occurrence of natural hazards. So the dynamics under the joint stochastic control become the following expressions. This time we have kx1 and 1 minus kx1 belonging to 0, 1 interval, with k1 y1 equal to 1 minus kx1. And those represent differentiated weighting of the torque once it is decomposed. So these are the simulation results. We can see that the variation is swinging a lot for the distances between the patches until the optimal stopping moment, where it is equal to 0.02. The optimal stopping time is found at tau equal to 0.57. After this optimal time, the variation in distances increases, as well as the standard deviation. The same goes for the distances between bioreserves and patches. There's a swinging, there's a stabilization, with the lowest variation of distances between bioreserves and patches at 0.57, which is tau star, and at this level, the value is of 0.02. Beyond, we have an increase in distances, in the variation of distances, as well as in the standard deviation. As for the shadow price, or the willingness to pay to preserve the connectivity of the network, it is swinging, it is decreasing until the optimal stopping time. Once again, at tau equal to 0.57. Its value is 32.02. Beyond, the shadow price increases, which is not supposed to be the case because it's supposed to be decreasing along the timeline, as well as the standard deviation. So we have the following results. The preservation of the ecological network architecture in uncertainty cannot be achieved under stochastic control over the entire duration of the forest management plan. It can only be accomplished at the cost of sacrificing the links between the patches by increasing the usage of the control devices. The optimal scenario in which the willingness to pay is the lowest and all connections are well preserved occurs at the optimal stopping moment, be it at half of the course. The optimal forestry policy thus has to shorten the timing of the protection devices to the biodiversity protection by half. A couple of concluding remarks. So this work aimed at providing a formal framework for the evaluation of financial resources needed to preserve the connectivity of an ecological network in uncertainty. Through the consideration of stochastic optimal control, we have been able to study the controllability of a random graph. By focusing on the optimal stopping moments, we have also shown that the optimal control of ecological networks is out of sync with forest management plans. Our findings go along with the discovery that biologically based rotations are typically 2 to 3 times longer than economic rotations for the same 3 species and site conditions. And our work permits to develop an awareness on the fact that the ecological sustainability depends heavily on the economic constraints. The management objective turned out to be part of a large decision-making process that needs to be inclusive of a variety of parameters. Thank you for your attention. I don't hear you. I don't hear you.
I didn't open the sound. So I think that I thank you a lot, and we just close the connection, and thank you again for and all the speakers for this nice conference. So thank you.